Hi. So this is a new chapter. Um, it is called medium scale integrated elements. MSI elements included logic circuits. So as you know, we categorize the logic elements. How we categorize them? SSI elements, single scale integrated circuit, that's the one. Medium scale integrated circuits, large scale integrated circuit, very large state. A single one has got 0 to 10 gates, medium up to 100 gates, and the large scale up to 1000 gates in it. So we know that gates are not available individually. You cannot buy a single AND gate, single OR gate, whatever the gate is. So we have the integrated formed gates. We know in single scale integrated circuit, for example, we've got 4 2-input AND gates within one integrated circuit. So these are the elements that we use in the lab. Now there are higher size integrated circuits. This is the MSI elements, medium scale integrated circuits. Among these medium scale integrated circuits, we've got decoders, that's the one, and we've got multiplexers, and in here you're saying switching operation. This is an example for the synthesis of a system by using decoders and multiplexer in it. This is a switching circuit. So we're going to see how to design a switching operation circuit by using decoder and multiplexer. That's going to be one frame here. The other MSI elements, parallel adders, there are subtitles for this, 4-bit. For example, if you go in, you could see that 4-bit adder, carry lookup, binary coded decimal adders, different type of adders in this frame, and the comparators. So you can compare two binary numbers, which one is bigger than the other one. You can make the decision by this element. So in these MSI elements, we will be seeing those elements. So altogether, we are going to have almost 5 videos. One of them is related with this decoder element now. So this video is related with this decoder element. Let's go inside to this decoder element. Let me clear some of the drawings here. So this element has got, as you see here, 3 inputs and 8 outputs. If you want to draw the truth table of this element, these are the inputs. So if you've got 3 inputs, the total number of different inputs that you can apply is 2 to the power 3, which is 8. So if you look at the outputs, we've got 8 functions. So this circuit has got 3 inputs and 8 outputs. If you look at the outputs, it is quite interesting. For the first line here, all the functions has got the value 0 except 1. If you look at the other one, for the second line, for this input, you might say, in other words, only one of the function has got the value 1, the others are 0. So if you consider one line here, for each input, you're going to observe one of these output lines here. Just by looking the output line, you can say what the input is. For example, if you are observing this output, then you can say that just the output, that means 3 of them, and output 6 is equal to 1, the others are 0. Okay? So you're observing this output. You can say that your input is this. So this is a binary number. So you are encoding it. You are decoded. This is a coded value. Coded. It could be any. It could be a statement. It could be a command in writing a program. So this is a coded information. So you can say which command is this, isn't it? Just by looking at the output. You can say that this is the 6th command. If you are observing this all zeros and this the last one is 1, so you can say that the input command is 7th command. So you can separate each command from each other by this decoder. We call it active output. Why is that? Because if you look at the output, all the functions are going to be 0 except 1. So just by looking at this one value, you are separating the command from the other commands. Therefore, we call it active 1. So the others is 0. That's why it is called active 1. Let's see now, this is what the circuit does. What is inside this circuit is quite simple. Look at this function now. This function M0 function has got one value only. For the other inputs, it has got the value 0. So if you write this M0 function, so it's going to be 1, this function, when the input is 0. That's this function. M1 is M1. 0, so it is 1, isn't it? So sorry. So input is 1, that is. M2 is 2, it goes like that. M7 is 7. Sorry. What it means, each of these functions has got one minterm, isn't it? That is a minterm. So we are writing the true minterms while we are defining our function. So what is written here is true minterms. So this function has, each function here has got one true minterm in it. So true minterms is the summation of the true minterms is the first canonical expansion, isn't it? So what this true minterm represent a product term. So this one, for example, represent a product term. What is this product term? X1 prime, Y prime, and Z prime. So this is the product term which corresponds to that true minterm. So since the other output values are false minterms, they are not going to be the same in this function. They are not going to be seen in the first canonical expansion. So that means the M0 is this then. M1 is this. M7 is going to be X, Y, Z. So the decoder output is decoder outputs represents minterms, all the possible minterms. So that's quite interesting. So if you consider this now as an input and output, so you might consider now this is a one MSI element. You are not going to design the inside here. We are just telling you what is inside of a MSI decoder. That is a decoder and MSI decoder within that box. We are not going to design this. This is available, so you can buy this decoder in the market. How you're going to buy it, you're going to say the size of the decoder that you are dealing with. So the size of this decoder is input is 3, that's the input, and the output is 8. output 8, input 3. So if the size of this decoder is 3 times 8, so size is explained like that. So if when you go and try to buy this decoder, you're going to ask for the 3 times 8 decoder I would like to buy. So they'll give you that decoder. Why we said active one? We said that, isn't it? We said if you look at the output, only one we've got. By looking at this one value, we can say what the input code is. That's why it is active one. We are not looking to 0 values to make that decision, just by looking for the one value of the output functions. So let's go one further here. In here we are going to examine another type, another size encoder, but this time this encoder is a smaller size encoder. So size is 2 times 4. So you're going to have 2 inputs and 4 outputs, 2 times 4. But this is different from the previous one. This one has got additional input. So if this is X and Y, additional input E here, it is called enable. And in general, enable. In general, this additional input is called control input. This type of inputs are not seen in SSI type of elements because you've got a very limited number of gates in it, so you don't need any control input. When you increase the number of gates within a circuit, that is MSI or LSI type of elements, you've got these additional input control inputs. So you can control which inputs you're going to control, you're going to make it effective, and you could do different, you could assign different functions to your MSI or LSI elements by using these control inputs. Therefore, we separate these inputs from the independent, among the independent variables, we separate these inputs as control inputs. The other inputs are the information inputs, you might call it. So this decoder then a bit different from the previous one. In the previous one, we didn't have any control input. This one, a smaller size, but it has a control input. So the total number of input is still 3, and the output is just 4. In the previous one, it was 8. So truth table, if you want to draw a truth table for this one, since the input is 3, it's going to be 2 to the 3 is 8 rows here. So enable X, Y, so it's going to be 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 1, 1, and then 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So the function of this enable input, when the enable input 0, whatever the other inputs are, you're going to observe at the output zeros, ones. For all of them, 1, 1, 1. So that means this is inactive. When enable is 1, it behaves as a 2 times 4 decoder. So you're controlling to run your decoder or to make your decoder active or inactive. In this area, it is inactive. It's not working, not functioning, let's say not functioning. And in here, functioning. So it behaves a 2 times 4 decoder. You see here we've got 8 rows. It's not easy to draw these rows, but we could reduce the number of rows by using this concept here. When enable is 0, whatever the other variables are, these represent don't cares. Whatever the x and y values are, your output is going to be 1, 1, 1. So that means you can represent these 4 lines here as just one line here. So that means you reduce the truth table. This reduced table is called function table. So this is a function table of a 2 times 4 decoder with an enabled function table is this. So we reduce the number of rows here. Apart from that, another property that we're going to see here is that it is active 0. Active 0 means in this area your decoder is not active, but in this area it is active. When you look at this active area, so you see one of the output is 0 while the other outputs are 1. That's why we call it 0 active. So you're going to observe this output and tell what the input is. You're going to observe that 0 and tell what the input is. So it goes like that. So what is inside of this circuit, you can easily say that consider that M0, this should have been capital M's. Why is that? I will tell you. So you can, if your function have got zeros and ones, so if you define a function, so you're going to set 0 points and the 1 points. So that means you're going to say min terms and max terms. So if you write the second canonical form for that M0, so it's going to be this, isn't it? So that means max term, that means true max term, 0 is this function. Why is that? There is only one 0 value for this function. So in the second canonical form, we write the true max terms. That means sum terms. Each 0 represents one sum term. What is this sum term here is, there's a mistake here, it should have been 0. X value is 0, then x itself. Y value 0, so this is the sum term corresponding to this true max term. This is true max term. This is the corresponding sum term. Okay. If you remember, if you write the, in order to write the second canonical form of a Boolean function, you're going to write product of sums. These sum terms, each of them represent a true max term. So in this case, we've got, in this function, we've got only one max term, and this is this max term. So it goes like that. Look at here. When you apply x and y here, so this is an NAND gate. So you're applying here the order should have been different, isn't it? So x prime and y prime is here when the enable is 1. So first, let's see, when enable is 0, all these NAND gates, one of the inputs 0 multiplied, 0 multiplied anything give you 0. Prime of that 0 is give you 1. So that means when enable is 0, your outputs are going to be 1. So we check that. If you consider this one, now we've got true max terms. All the possible true max terms are here. And there is a mistake. This should have been x plus y, isn't it? But because prime comes in. So this is x plus y, that is x plus y prime, that is x prime y, and that is x prime plus y prime. So why is that? You see here, that's x, and that is y. So this is the NAND gate, x times y, complement of it, isn't it? So that's the NOT. So that gives you x prime plus y prime. When enable is 1. When enable is 0, that's going to be 1, isn't it? So that is the decoder that we are talking about. So we said some MSI elements has got a control input. The outputs could be active 0 or active 1. So in here, active output is 0. In the previous one, for this one, that was 1, isn't it? So this is active 1, and this is active 0. So we mentioned about the function table and the truth table. So if you write the proper truth table, you're going to have many rows. For this case, 2 to the power 3 rows. If you use the function table, it's going to be just 5 rows. And let's come to the other. How we use that enable. We said we've got an enable input, control input, and we said this input is from time to time we might need this input. One of the application of that enable input usage is the increase the size of the decoders. If you got 3 times 8 type of decoder, how you can find out a decoder with that size 4 times 16. So that means you got 4 inputs and you've got output 16, 0 to 15. So how I can get a decoder like that, a higher size decoder, by using lower size 2 decoders. If you consider the enable input, by using this enable input, you can increase the size of your decoder by using lower size decoders. So look at this now. So these are the variables x, y, z, and I'm going to use this W independent input variable as an enable input. So if the W is equal to 0, then this is a NOT gate. The output is going to be 1 here, and the second decoder enable input is going to be 0, isn't it? So when this enable is 0, this decoder is not going to work, but this decoder is going to work. So if you consider this as the truth table case, W, X, Y, Z, so W is 0, and these inputs from 0 to 7, so that means totally 0 to 8, you get the output M in here M0 up to M7 at the output of the Z. So what's going to be these outputs? These outputs are going to be 0, not effective. So consider the second part of your truth table. Change the color of it. When W is equal to 1, so that means this input is going to be 0, this decoder is not going to work, and this decoder is going to work. Why is that? Because W is equal to 1, so that is 1. When it is 1, this works. When this works, that means W1, X, Y, Z from 0 to 7, and I'm going to have here M8 up to M15 output. So you see, if you consider this now 4 variables and the 16 outputs, that's that decoder. How I made this possible? by using this enabled gate as my last input variable. So this is how it works. There is a question here. You're going to consider this one. It says you're going to design a 4x16 size decoder by using not 3x8 decoders, but 2x4 decoders. So the smaller size. So you're going to make the decision how many of those you need and how you're going to connect them together. So you do analysis and then synthesis to get that. So this is a problem left to you to solve. All decoder sizes. Go a bit further. Now, another usage of these decoders in practice is the design of logic functions we could use. How we could say that we could use that? Because we know if you got a decoder, at the output of the decoder, you got all the possible minterms. So in here, this is a truth table for a full adder. Full adder, you see, has got 3 inputs and 2 outputs. One of them sum, the other one is the carry. So how I'm going to design this? If you design it by using the decoders, we are going to do it right now. We have done the design of this full adder by using the SSI elements. We already done it for SSI elements. But in here we will be using the MSI element. You see the carry function here is this function, isn't it? So for minterm 3, 5, 6, and 7, this becomes 1. That's why these are the true minterms. For these true minterms, my C function is equal to 1. This is first canonical expansion. So all these true minterms, all these minterms in this function is available here. 3, 5, 6, 7. So if you connect these true minterms to an OR gate, that means summation of those, isn't it? 3, 5, 6, 7. So these are product terms. Sum of these product terms, is going to give you your function. So that's the carry function. Similarly for this one, let me change the color. So that is 1, 2, 4, 7. 1, 2, 4, 7, that is 1, 2, 4. So you see 4 here and 7 here. 0, 1, 0, 1, 2, sorry. So that's not, say, let me clear this. 1, 2, 4, 7. So if you do this connection, 1, 2, 4, 7. So you got to, I made a mistake. This one for carrier. For this sum 1 to 7, here you are 1, 2, 1, 2, 4, 7. So that's the sum function. What we have done, we used same decoder for the design sum function and also for the carry function. So we are sharing this decoder now for those two functions. So if you are designing more than one function, if you need to design more than one function, so that means you're going to design a logic circuits which has got more than one outputs, more than one function, then you're going to use for each output function one OR gate, isn't it? If you got one, let's say, m number of functions to be designed. For each function, you're going to use one OR gate. For all these functions, you're going to use only one decoder, because decoder gives you all the possible minterms. Among these minterms, for each function, you're going to separate the true minterms for this function and connect these true minterms to an OR gate in order to get that function. So you're going to continue, you're going to do the same thing for all these functions, and you're going to design that. So this is a good element to design a logic circuit which has got more than one function at the output. The cost of this design is only one decoder that you're going to use. For each function, you're going to use additional OR gates. That is the rule of designing a logic circuit by using decoders. There is a good question here, so you can answer to that question. Does number of function to be designed affect the decoder number to be used? So you answer to that question. So MSI design, no need any SSI design technique, Koymakles Karno map to apply. So we didn't find any minimal function while we are doing the design of these functions here. So you can compare now this design with the SSI design. Which one is better? Which one is simpler? Why? And what is the cost difference also? You can say all that. So this is a function synthesis by using decoders. We examined that. And let's come to another MSI element which does the opposite of the decoder. It is called encoder. Encoder has got 8 inputs, M0 up to M7, and 3 outputs. So in the decoder, the inputs were 3, outputs were 8. In this case, it is the opposite. Inputs, 8 inputs, and 3 outputs. So in practice, we need such an element. Why do we need it? Consider your keyboards that you are using, your PCs. On the keyboard, you've got different symbols, isn't it? For these different symbols, assume that these symbols are sent to the computer. Computer a digital equipment, isn't it? It accepts only zeros and ones, not the other signals. So your symbols is different from zeros and one, so your computer doesn't accept your symbols that you send here. So for each symbol, you've got to send different code to your system. This code must have zeros and ones only. So this is called encoding. So each symbol on your keyboard are going to be encoded to separate each one of them from the others. Okay. Now look at here. Assume that you've got 8 symbols. So this symbol's M0 to M7. So how I am going to separate these symbols from each other? So if you look at any line here for example, so that is the symbol M4, isn't it? That means you push that button on your keyboard. So that means you are dealing with this symbol. Assume that this symbol is F. Then your output code is this. So that means when you push that button on your keyboard, the signal sent to the PC is this. So this is encoded F, isn't it? F has been encoded as this. So this signal is accepted by your computer because it has got zeros and ones in it. So that is the encoder business. So if you look at whole truth table here, you might say that you've got 8 inputs, or in this case, each one of them represent a symbol. In the Boolean algebra case, the number of rows that represent by these variables is going to be 2 to the power 8, which is 256 rows. But in here, we are not using of all these rows. Why is that? Because in each row here, only one included here. The others, they are all zeros. That means you are separating each button in your keyboard, isn't it? Each one represent one button on your keyboard. Therefore, we are accepting these inputs, not the other inputs. The other inputs are not going to be applied, it means. Therefore, we didn't draw all others, because in practice, you're going to push one button only, not the other buttons. Each time you're going to push one button only. So this represents these inputs, and these are the related codes. Now, what is inside this MSI element is this, how we can make it like this. You could look at this X output. These are where the ones are, true minterms. So that means input M4, M5, M6, M7. Your X output becomes 1, isn't it? So these are the inputs. So M4, M5, M6, M7, when you add them up, add this one, you got this X, isn't it? So this is M4 plus M5 plus M6 plus M7. It goes like that. So you can represent each function by using a two-level OR gates here. So this is what is inside of an encoder MSI element. Okay. So you could see this. So that is end of this video. We can say that what we have seen here in this video, two MSI elements. One of them is decoder, the other one is the encoder, and we use those for the design of Boolean functions, increase the size of the decoders by using the enable input and the encoder, which is a useful MSI element to be used for transferring keyboard symbols to computer, as this is encoder. That's the end of this video then.